All right, so last week the material we are going to look at is on what's called vectors. So is anybody in physics, or has anybody studied vectors in another class besides physics if you're not in physics? Yeah, are you in physics?
I had discrete math last year.
Okay, yep, so you definitely did vectors last year. Yep. So the idea of vectors is it's a quantity that has a magnitude to it and a direction. Okay, so what does that mean? Well, let's say, for example, we are measuring velocity. Okay. Every picture, every plane that you see on this diagram has a velocity to it. Okay. Velocity just doesn't mean how fast it's going. Velocity means two things. It means how fast is the plane going and in what direction is it going. So if you want to represent those two things at the same time, a vector is how you do it. Okay. So if you told me the vector of that plane, say right there, that would tell me the direction that it's going and the speed that it's going. And if we click on, well, I want to click on one that looks like it's moving. I think I just saw that one move. That one could be on the ground, just parked. So this particular plane looks like it's heading towards Boston. And if I look over here, it tells me the speed of the plane. So that's part of its vector, 412 miles per hour. And the other part of its vector is this route. Now this is a little more complicated because the plane is changing directions a little bit. Overall, its directions that it's going are mostly between like 80 and 100 degrees. That's most of the outbound course. 90 degrees is to the right. Okay, that's east on a compass. I know we do 90 degrees as being up. That's not really how a compass works though. Okay, 90 degrees is to the right. So I can see all the headings. This plane is pretty much traveling to the right. Occasionally, if it goes past 90, that's a little bit south. If it's above 90, that's a little bit north of east. But in general, it's heading to the east. So if I combine the direction that it's heading with its speed, that would give me the vector for the plane. Okay, so that's one use for vectors. Trying to coordinate all this traffic. It doesn't look like there's a lot, but if you start to zoom out, you definitely see, I have to go back to the computer, but you start to see a lot more planes, hundreds, thousands of planes all in the air at the same time. Now if I zoom out, you can see a lot more. And as you start to zoom out, I think some of them even disappeared. Yeah, you can see how many there were, and then they kind of like disappeared, so it didn't look like there were as many. But yeah, they got to coordinate all the different traffic, and one way that a computer can represent all the planes is vectors, and it can make sure that all the planes are, in theory, like a safe distance apart. And it might look like these two planes are pretty close, but I mean they could be like 5 miles apart. We're zoomed out to seeing half the country here. So, yeah. And notice there's no planes around in this area, probably because that's, it looks like there's a storm there. So that could force a lot of planes to be a little bit closer because they're trying to go around that storm. All right, so that's one example of a vector. Okay, another example is force. So when you exert force on something, like if I was pushing on this board, if you wanted to describe how you were pushing on it, you're going to tell me two things. How hard are you pushing, and in what direction? There's a difference between pushing to the right and then pulling to the left. Those are the main two examples that we're going to focus on. If you had discrete, or if you've taken physics, you probably do a lot more applications than we do. Okay. So the simplest way we can represent a vector, if you want to do it as a visual, is with an arrow. Okay, an arrow is perfect because it points in a certain direction. When you write something as a vector, direction is one of the things you need to tell me. While an arrow is perfect. Right? You just look at the way the arrow is pointing, and that tells you direction. What do you think I could change about this arrow to represent magnitude? That's like the speed the object is traveling at. Like, How do you think I could represent an object traveling faster? Yeah?
Longer arrow.
Longer arrow, yes. So the longer you make the arrow, that means the faster the object is going, or if you're talking about force, the harder you're pushing or pulling on something. So that was one plane, and that was the other plane. Both of those planes are going to the east, but the bottom plane is going twice as fast. If those were forces, that means somebody is like pushing to the right, and the other force is twice as strong in the same direction, to the right. An arrow isn't always the fastest way to do it. If we want to start to do things faster with vectors, we don't want to be drawing them every time. Drawing is good when you have a word problem, so you can kind of visualize it. And drawing's good when you're starting out, because it gives you a visual every time, and it makes it more like concrete to understand. But it is not the fastest way to work with vectors. Okay. So any question on the fact that the way the arrow points is the direction, and the length of the arrow is the magnitude? So let's say that we had 2 points, and the vector started at one point and went towards another point. Right? When you, in geometry, when you learn about drawing something from one point to another point, usually we call that a ray. Right? That's kind of like what a vector is. It's like a ray. The difference is, in geometry, a ray goes on forever. When we talk about vectors, they don't go on forever. They stop. If it went on forever, that would represent like something going infinitely fast. It's not really something we deal with. So that is one notation you can use. Okay? That notation for the vector borrows the notation from geometry. That's the notation for array. A more common notation, I'm going to show you in a second. A more common notation is just to use a single letter rather than like PQ. So let's say that we start at point P and we go towards point Q. That's my vector. There's the length of it, and that direction it's pointing is up and to the right. I can call that vector a single letter. Okay? I can name it with just a letter. The problem is we already use letters for something else in math. What do we already use letters for? Yeah? We already use letters for variables. Well, variables and vectors aren't the same thing. Okay, so if we're going to use a single letter, we need to make sure it looks different than a variable. And there are 2 ways we can do that. If I wanted to name this vector M, I can either call it M and put a line on top, or put an arrow on top. That's one notation you can use when you name a vector. Or just make the letter bold. Okay? And that's the one that you're going to see in our book most often. Okay, so anytime I refer to a vector in this section by its name, I either have to give it a letter with an arrow on top, or I have to make the letter bold. As far as the letters you can pick almost any letter you want. There are 3 letters you are not allowed to pick. You cannot pick I, J, or K. If you want to pick any other letter, that's fine. I would probably avoid letters that look like numbers, like the letter O. That could be confusing because it might look like a 0. But technically any letter other than I, J, or K. Does anybody know why we can't use I, J, or K? It doesn't have to do with them looking like anything else. Yeah?
Isn't I used for imaginary? Like something's imaginary?
Okay, so a lot of times we do use I when we're talking about imaginary. In this unit, whenever we write I, we're going to forget about imaginary. So unfortunately, that happens in math. Sometimes you do use the same letter for different things, and they do that here. So we are going to use the letter I, but it has nothing to do with imaginary. So we're going to totally forget about imaginaries. So if you're not sure why, I'll show you either later today or probably tomorrow why we don't use ij or k. So first thing we're going to look at is what happens when you add two vectors together. So let's say you had a boat and you had a fan blowing in that direction. Well, if you do that, then the boat would go up. But what would happen if I put two fans on it? One blowing up and then one blowing to the right. What direction would the boat go in? Yeah?
Northeast kind of?
Yeah, it would go like northeast. It would go up and to the right. If I want to know what the vector would look like for the boat, this is what I would do. And I'm going to show you how to do this in a second. That vector in black represents the combination of the two in red together. So the important thing to understand is when you take a vector and you add it with another vector, you get a new vector. So that's important. When you combine two vectors together, you get a new one. The new vector can have a different direction than the two original ones, and this one does. This one goes up and to the right. The original one went up. The second one went right. So that's a new direction. And it can have a new length. And if you look closely, I don't know if you can tell, but the black one is longer than the red ones. Okay. The way I could show it is if I rotate it. Well, if I were to rotate it like straight up and down, then you can see that it's a lot longer. Okay. And if I put it right, you could see it is longer than the right one as well. So combining two vectors together can result in a longer vector. It could be a shorter vector. The point is the length can change. Okay, so how do we add them together? Well, you do exactly what I just did right here. You've got to line them up like that first. So the way you line them up is you make sure that the end of one of the vectors and the beginning of the next one, put those 2 points right on top of each other. Another name for this, it's called connecting the vectors head to tail. Connect the head of one vector to the tail of the other. It means the beginning to the end. All right, so let me draw two more. Let's draw one like that, and one like that. And let's say I want to add the black vector and the green vector. So I'm going to line them up. So the ending point of the first vector, let's call this one vector v. That's supposed to be bold. And let's call the green one w. Line them up so the end point of v and the initial point of w are right on top of each other. Just like that. Okay. Any questions on how I line them up? That's the first step. Now the last step is to connect where you started to where you finished. Right, so the new vector is found by connecting the starting point of the first one, so the starting point of the v, and the ending point of w. Start of v, end of w, and make a straight ray between the two. Just like that. So that is what v plus w looks like in this case. So it's not really doing anything numerical. It's not finding the actual numbers for anything. It's drawing an image. That's the answer to this kind of question. It's a sketch. Once we start getting beyond sketches, then we can do this with just numbers, which is faster. Numbers are faster. All right. So let's, I got an example. Right there. So let's add V and W together. If I want to add these together visually, what's the first thing I have to do with these two vectors? I think they can describe to me what I need to do. Yeah.
The endpoint of one on the other.
Yep, and let's do it in the order V first and then W. So let's take the end point of V, which is where the arrowhead is, and take the starting point of W, which is where the arrowhead is in, and line those up just like that. V plus W on the end of it. Okay, so now I lined them up. And what's the last thing I have to do to get the actual answer? Yep.
Start from the initial point of V and draw a line to the end point of W.
Yep, start from V and go towards W, just like that. And that is your answer, right there. There is an arrowhead, I don't know if you can see it. Any question on that? Fine. Let's try this one. Okay, before I do it, anybody have an idea what's going to happen? Yeah?
They're gonna cancel out.
Okay, so these are going to cancel out. But we know when we add two vectors together, you always get a new vector. So when you write your answer to this, it has to be a vector. So we need to figure out how we're going to do that. Okay. If you're not sure why they cancel out, well, let's look at it. You need to connect the end point of V to the start point of W. So in other words, line up the blue dots. The end point of V to the start point of W. Once you line the blue dots up, then connect the start of V to the end of W. Okay, listen. So you're going to line the blue dots up, and then when you're done, connect the green dots, starting with that green dot and drawing to the second green dot. So let's line up the blue dots first. So I line the blue dots up, but once I do that, the green dot's also lined up. So there is nothing to connect here, because they're the same point. Well, the way I'm going to write the answer to that, I can either write it as a bold 0, or a 0 with an arrow on top. What that means is the 0 vector. It's a special case. Technically, it's the only vector you can't draw because it has no length to it, and it has no direction. So it's a special case. But that is how you represent the case where two vectors combine together and cancel each other out. If you just put the number 0, that is wrong. When you combine two vectors, you need to write your answer as a vector. So it's not the number 0, it is the vector 0. Any question on that? Okay. So now, I'm not going to do the second one. You can write it down, but we're only going to demonstrate the first one. The idea of the commutative property is if you change the order, it doesn't affect the answer. What type of arithmetic does that property work with? Where you can change the order and you still get the same answer. Yeah?
Addition and multiplication.
Yes, commutative property works with addition and multiplication. And in our case, we're going to talk about addition. When you add vectors in a different order, you get the same answer. So let me show you that. So first, let me do V plus W. That's V. And if I put W on the end, that's V plus W in that order. Now, draw in an arrow, and that's the answer for V plus W. Any question how I got V plus W? Now I'm going to reverse it. I'm going to do W plus V. So take W, and this time put V on the end of it. That is different than the picture I had before. Now, draw your answer. That's W plus V. But if you compare the two of them, they are, I didn't draw it perfect, but it's pretty close. They're the same thing. So the order that you add vectors in does not make a difference. And if you had, let's say something like that, and then like that, you can add vectors together with 2, 3, 4, however many you have. If you want to add all these together, that is one way to do it. Black, red, purple. And watch what you get for the final answer. Okay, we get that one in green. Let me do them in a different order. Okay. So instead of black, red, purple, let me do red. Let's just do something different. Let's do red, purple, black. So let's put black on the end. That's a different order. But look at how the answer compares. It's exactly the same. So you can stack as many vectors as you want together to add them up. Just make sure, kind of think of it as like a one-way flow. Okay? Like the way drainage, plumbing should work in your house, right? When it's going, it should always go one way. If it goes back the other way, you got issues. All right, so all the arrows have to flow in one direction. Okay. So that's commutative. And associative, I'm not going to draw this one out. Associative doesn't have to do with the order, it has to do with the grouping. You can group how you add them together differently, and you still get the same answer. Right, so same order on each side, A, B, C. But the difference is I'm doing A plus B first on the left, and on the right I'm doing B plus C. It doesn't matter. It'll come out exactly the same. Okay, and you might think, well, yeah, don't we always use these properties when we add? Yes, but we're adding vectors, and we don't. If you haven't worked with vectors, you can't assume that all the properties that you know right now, like distributive, all that stuff, you can't assume that any of that works with vectors. Because vectors are something new we haven't studied. But these two do. Okay, so this one I already kind of showed you guys earlier. If you have two vectors, and one of them goes in the opposite direction as the other one, but it's the same length, they cancel each other out. And you get what's called the zero vector. So if I were to draw this and that, what would be the only difference between the two of them? The vector v and negative v. Yeah?
Will be in the opposite direction.
Yeah, that's the only difference. What would be the same between these two vectors?
There. Has an
Okay, they both have arrows. We know they go in opposite directions, though. But there's something else that would be the same, yeah?
Magnitude.
The magnitude, the length of them. Yep. If you were to measure each arrow, they'd be exactly the same length. So the only difference is that they point in opposite directions. All right, so any question on how we can add two vectors visually? Now we're going to do subtraction. Let's start out with a problem with numbers. 3 minus 2. Let's say you were trying to show someone how to do 3 minus 2. and they don't understand subtraction, but they do understand addition. They understand how to do everything with addition. How could you change this problem into an addition problem? Instead of thinking of it as 3 minus 2, give me a different way to think about it. That's the same thing with addition. Yeah?
3 plus -2.
Yeah. 3 plus the opposite of the second number. That's how you do subtraction. Subtraction is just addition of the opposite. And that's exactly how we're going to do subtraction with vectors. We're going to do addition of the opposite. So what does opposite mean when we're doing vectors? It means you've taken the vector and you flipped it around. That's the opposite. So other than just having to take something and flip it around first, subtracting two vectors is just as easy as adding. Find the opposite of the second one, and then add it. All right, so let's see if we can do v minus w. Okay. So, how can I think of v minus w as addition rather than subtraction? Let's start just by rewriting that. Yep.
I was just gonna say you could go the opposite way with it, but I really don't know anything after that. Like how to figure out like v minus w. You know how you like go one way for that, you just turn it the opposite way. Now it's
Okay, so we're gonna turn something the opposite way. And what does that mean? How are we gonna think of it when we write it? Yeah?
V plus -w.
V plus W turned around. Yeah. V plus the opposite of W. So first thing I need is the opposite of W. Well, on the smartboard I can do that easily. If I take something and I flip it left to right, and then you flip it again up to down, it will automatically make it point the other way. That's the same as rotating 180 degrees. I don't have a rotate 180 button on the board. So that's how I do it. All right. Any question on how I got negative W? Now, we're going to take V and we're going to add negative W. So take V and put negative W on the end of it. That's V minus W. And then the last thing is just to connect it. I'm a little off, but not. That's pretty good. That's V plus negative W. Make sure you make your arrowhead big enough so you can see it too. All right, that's subtraction. Any question on that one? So next thing, so that was adding a vector to a vector, subtracting a vector from a vector. The next thing is going to be what's called a scalar product. If you have a model of something and you build a scale model, what does that mean? If you compare like a scale model to the original, what's the difference?
Smaller version.
Could be a smaller version. What else could it be?
bigger.
Could be bigger, yeah. Like if you were making a model of, like in chemistry or something, like a model of an atom, you're probably going to make a bigger model, right? It's already pretty small. You're not going to make a small model. So you're going to make a bigger model. But if you were designing a house, you might make a small model, like on a foam board or something, so a client could see what you're going to build. So a scalar product is when we take a vector, like v, and we multiply it by a number. What do you think multiplying v by 3 would do to it? Yeah?
Triple it.
Yeah, it would make it 3 times as long. Yep. So when you take a vector and you scale it, this number in front is called your scalar. And what the result is a new vector. It can be longer, it can be shorter. There's also one more thing that could happen. If this was a certain kind of number. Anybody think of the other thing that could happen to it?
You put negative in front of it?
And what do you think putting a negative would do?
Flip it?
It would flip it around. Yep. So when you scale a vector, the three things that can happen, it can get longer, it can get shorter, or the direction can reverse. I mean, I guess if you scale it by 1, it would stay the same. Okay, so let's take a vector and just practice drawing a couple scalar products. So that's what this is called, scalar product. Okay. So I've got V. How could I find 2V on the board? I want to do this as exact as I can. But I don't have a ruler to measure anything, so I'm not gonna actually measure. Yeah.
Make a duplicate and then like add it on to the first one and then
Yeah.
make a new line or something.
Yep. So just take 2 of them, stack them together, and then just draw your answer. So this is 2V. Just like that. Now, half V, I don't have a way to do that one exact, but it would point in the same direction, but it would be half as long. So maybe about like that. So that's half V. So in one case it got longer, one case it got shorter. What kind of number do you think you would scale by and it would get longer? Your number would have to be more than 1. Yeah. More than 1. All right, let's try this one. So this time,
It's not working. It says like, that's not up there. There's no map.
Mouse is already being.
oh shit. Oh yeah, you can use the mouse. Did that work when you clicked on it?
Yeah, there we go.
Okay. We're good now?
Yeah.
All right. Okay, what's going to happen with that first one? Yep. Yeah, and I could do it exact, but I'm just going to kind of estimate it. So it's going to flip direction. But what didn't change when you multiplied it by -1? The magnitude. It just flipped the direction. Okay. And then for -1/3 V, well, the first step is to flip the direction, and then the second step is to make it 1/3 as long. Well, I already got the direction flipped, so just take that and estimate about 1/3. If we were doing it on graph paper, we can do it exact. Okay, any question on that one? So what kind of product is that called again? Scalar. Yeah, scalar product. Longer, shorter, or flip. All right. Now let's combine an addition problem with a scalar. Okay, so the first thing I'm doing is I'm adding 2V and 3W. So what you want to do right away is figure out 2V. So let's take V, make a copy of it, and put them together just like that. There's 2V. And what do I need to put on the end of 2V? 3W. Do I need to flip the W around? No, I'm not subtracting. So just take W, make sure you have 3 of them, and stack them all together. All right, so that's the picture you would draw, but we have one more step to get the final answer. Yep.
Beginning of V to that.
Yeah, connect the beginning of V all the way to the end of W. And that's the answer for 2V plus 3W. Now, this one, you're starting to get into what can happen. If it was like 50V plus 600W, I don't have enough space to add that all up. So that's one problem with doing it visually. It can go off your graph paper. Okay. Any question on that one? All right. When we are starting to do things with vectors, if we want to do them a little bit faster, we need ways to start doing things without drawing as many pictures. Right now, the way we have to represent magnitude is to draw an arrow and make it longer or shorter. If you want to represent the magnitude of a vector, you put two vertical lines around it. This symbol means magnitude. And the answer to that is a number, 5, 6.5, whatever the length of the vector is. Magnitude is always positive. You cannot have negative distance. If you measure the distance from here to the door or the door to here, it's a different way to measure it, but it's not negative feet if you measure it a different way. Okay, magnitude is always positive. So knowing that, what would be the difference between the answer to that and the answer to that? Nothing. There is no difference. Sometimes people say, well, one's negative and one's positive. Nope. The final answer to that is a positive number, and the final answer to that is a positive number. Okay? It's asking for the magnitude. So they are exactly the same thing. The vector that you're taking the magnitude of is different, but the actual magnitude is the same. Now, if the magnitude comes out to 1, the vector has a special name. Does anybody remember when we talked about circles with a radius of 1? We called it a blank circle. Called it a unit circle. So what do you think we call a vector that's 1 unit long? It's called a unit vector. And that is starting to get into why you can't use ij or k as letters. I, J, and K are special vectors. Okay, they mean something. They are what we call unit vectors. But I'll get into that more tomorrow. Okay, for today, all you need to know is if something's 1 unit long, it's called a unit vector. So that is one thing. When we do study vectors, this first section, there's a ton of vocabulary. Unit vector, magnitude, direction, lots of different vocabulary. All right. So if we want to start doing adding, subtracting a little bit faster, we got to figure out a way to do it without drawing pictures. Okay. Not saying a picture isn't good. It is good if you're just learning and you're trying to really visualize what's happening. But if the goal is just to add two vectors together, we can do it a lot faster without drawing. There are two notations that I'm going to teach you for how to represent vectors without pictures. The first one is called the algebraic notation. That's how our book refers to it. And an algebraic vector looks something like I just picked two random numbers, but that's an example of what a vector looks like in that notation. Okay, so what's going on there? Well, we've got two numbers. We've got a comma between them. What other thing do we write down that has two numbers and a comma between them? Yeah?
Coordinate pair.
A coordinate, yeah, coordinate pair. So we want to make sure when we write a vector, it looks different from a coordinate. The way we do it is we put these in angle brackets, kind of like a less than and a greater than symbol. We put those on the ends, and then we know It's a vector. So what does each number mean in the vector? Like what's the 4 and what's the 5? The 4 and the 5 are what we call components of the vector. Okay. So let me show you right here. And I'm going to scroll back up, so don't worry. If I wanted to draw the vector 4, 5, I can put it right there. What the 4 means is that is the horizontal component. That means to get from here to here, I need to go 4 units horizontally, and the 5, second number, that's the vertical component. That means I need to go 5 units up. So you can think of the 4 and the 5, it's like directions, how to get from the initial point to the terminal point. So the A and the B, which is what I call them up here, those are called the components of your vector. Since we're dealing with 2D, we only need 2 numbers. The first number is your horizontal, the second number is your vertical. When we get to 3D, we need a third number. And the third number is like what comes out of the board. That's the 3D part. All right, so A tells you how far left or right you need to go. And B tells you how far up or down you need to go. So it's like directions from the initial point to the terminal point. If A is positive, you go right. If it's negative, you go left. Just like you're graphing a coordinate. If B is positive, you go up. If B is negative, you go down. Now, what I just drew there, the vector, that arrow that you see, that's that, 4, 5. But I could also take that and I could put it over there. That's also the vector 4, 5. That's the vector 4, 5. And I'll put it over here. That's the vector 4, 5. They're all the vector 4, 5. What this notation doesn't tell you is where to put it. You can put it anywhere you want. So if I said to you, draw the vector 4, 5, any one of those is correct. Now, there is a place that's most common to put it. Where do you think the most common place to put it would be? Yeah?
The origin.
Right, starting at the origin. And if a vector starts at the origin, it has a special name. That is called a position vector. That's a vector that starts at the origin. It's called a position vector. So let's erase most of these, and let's just leave that one. Now, we already know the vector. It's 4, 5. But what I want to do is see if I just told you where it started and stopped, could you figure out that it's the vector 4, 5? Well, if you've got a picture, yeah, you can just count. 1, 2, 3, 4, 1, 2, 3, 4, 5. But we're going to pretend like we don't have a picture. And all we have are the coordinates for where it starts and where it stops. What's the coordinates for where that vector starts? 2, 5. 2, 5. And what's the coordinates for where it stops?
6, 10.
6, 10. Yep. Now remember, we know the answer is 4, 5. Does anybody see a way that you can take this coordinate where it starts and this one where it stops and somehow do some arithmetic and end up with that is the answer? Yeah?
Subtract the endpoint. No, subtract the starting point from the endpoint.
Right. Subtract, take the terminal where it ends and subtract where it starts. So if you do 6 minus 2, that gives you the 4. And if you do 10 minus 5, that gives you the 5. That is how you find a position vector. You subtract the coordinates, but it has to be the endpoint minus the start point. When you subtract, does the order, would it matter if I do it the other way around? Yeah. If you do it the wrong way, you're going to get a vector that points the opposite of what you want. So instead of getting this answer, you're going to get that answer. It'll be backwards. Okay, so to find a position vector, the first thing you need is the initial point and the terminal point, and you subtract them. Terminal minus initial for the x's, terminal minus initial for the y's. That's it. All right, so let's see if we can find a position vector. If I don't tell you the initial point and the terminal point, and I just use like a P1 and a P2, always assume P1, first point, is the start point, and P2, that's the second point, that's the stop. Okay. So, starting point, stopping point. Find the position vector. What's going to be my calculation to find the horizontal component of my position vector? Yep.
X2 minus X1 minus 2 minus
So just say it again.
X2 minus X1.
Yep. What's x2 in this case?
So 4 minus -1.
4 minus -1. And what's the calculation for my vertical component?
6 minus 2.
6 minus 2. Basically what you're doing is you're finding the length of each side of a triangle, a base and a height. And when we simplify it, 4 minus -1 is going to give me 5. Yep. And 6 minus 2? 4. So if you wanted to draw this vector, but start at the origin, you would go 5 units right, 4 units up. And that's how you draw it. Okay. Any question on that one? That's finding a position vector. All right, so we just looked at a way to write a vector in what's called algebraic notation. You use the angle brackets, put in 2 numbers and a comma between them. The last notation we're going to look at is called unit vector notation. This is the most common way to write vectors without drawing. So just as a reminder, can somebody remind me again, what's a unit vector? What does that mean? It's a vector with a magnitude of 1. Yep. So we're going to look at 2 special unit vectors. The first unit vector is called I. I, whenever you're talking about vectors, is defined to be a vector that is 1 unit long and it points to the right. That's what I looks like. You can't name a vector I and have it mean anything other than what I just circled. I is always that picture. J is another special vector, and if you name a vector J, then it has to be 1 unit long and it has to point up. I and J cannot mean anything else when you're talking about vectors. Now, there's one other one which I'm not going to mention here, but I think I mentioned it earlier. What was the other letter I said not to use? Yeah, said not to use K. That's for 3D. We're not doing 3D till Wednesday. So J is always that picture right there. That's J. And the idea of unit vector notation is you stack i's and j's together to build your vector. And I'll show you what I mean. So think of I and j as they're like Legos, like building blocks. They're the smallest building block we have, and we can stack them together to make anything that we want. So let's see if we can build the vector 3, 4. Okay, first, let me just draw it. Okay. When I have that notation, does it matter where I put the vector? No, that notation, remember, it doesn't tell me where to put it. The most common place is the origin, so I could put it there. But I don't have to. I can put it anywhere I want, as long as I go 3 units right and 4 units up. That's the vector 3, 4. Now, I want to see if I can build that out of i's and j's. I'm going to stack them together. Let's start with the i's. If I want to get from this point to that point, how many of these i's would I need to stack together? I need 3 of them. So I'm going to make 3 copies. And then I'm going to stack them all together. 1, 2, and 3. So now, on the bottom, you have this. What is that vector in blue? Yeah? 3i. That's the first part of the notation when you're writing it as a unit vector. It's 3 i's stacked together. And then how many j's do I need? 4. I'm just going to draw them by hand this time. So there's one of them, 2, 3, 4. So now, going up, I have this vector. What is that vector in purple? That's 4j. So, if you take this vector in blue and this vector in purple, and you add them together the way we learned in the first part of the notes, you will build the vector 3, 4. 3i plus 4j. And that is all there is to unit vector notation. So it's basically like the algebraic notation, except take out the comma, get rid of the angle brackets, put an I after the 3 and a j after the 4. Now, I points right and j points up. So using i's and j's, we can really only draw vectors that go up and to the right in some way. What would I have to do if I wanted to draw a vector that goes left or down? Yeah?
Make them negative.
Yeah, if you make i's and j's negative, then like, let's say you wanted to get from here to here. Well, to do that, you would need 1, 2, 3, 4 i's going to the left, which means you need negative 4i, and you need 2 j's going down. What would this vector be that goes down? Negative 2j. So that vector in black is negative 4i minus 2j. So by making I and j negative, you can go left, right, up, or down. You can go any direction you want. If you ended up in the middle of a block, like that, that's fine. You can do 2i plus half a j. You can do a half j or whatever part you want to use, fraction of a j. Right, so that's unit vector notation. And that's the notation we're going to stick with mostly for the rest of the week. Any questions on that? All right. So how about this vector? Let me zoom in so you can see it better. How would you write that vector using unit vector notation? Yep.
6i minus 2j.
Yeah. 6i and minus 2j. Yep. And how would you write that vector if you wanted it in that notation instead? Yep.
6 negative 2.
6, negative 2. Both notations are correct, just a matter of which one they want you to use. Okay. Any questions on that? All right. All right, so that is the homework, and that covers everything we just did. So 1, 8 to 22, even, and 26 to 32, even. This last part is where they talk about the IJ notation. All right, so we'll take a look at that tomorrow. Okay, we're kind of in the middle of the second part, so we'll finish that up tomorrow, and we'll start looking at the third part as well.